Challenges and opportunities of carbon nanomaterials for biofuel cells and supercapacitors. Personalized energy for futuristic self-sustainable devices. By Jirapan and Nicholas Ma. Hello everyone, and welcome back to the .itthipium podcast, episode 2, where in this episode, we discuss science, engineering, and technology. In today's episode, we are going to focus on supercapacitors for personalized platforms. Yes, focusing on supercapacitors for personalized applications, such as wearable and implantable applications. A supercapacitor is comprised of electrodes, electrolytes, and usually a separator, separating the positive and negative electrodes, as shown in this figure. Mechanisms of supercapacitors can be classified into two main categories. First, an electrostatic process, double-layer capacitors, and, second, an electrochemical process, pseudocapacitors. In addition, hybrid capacitors can also combine both electrostatic and electrochemical processes. The electrode materials, particularly carbon-based materials, are significant toward the storage performance of supercapacitors. For instance, double-layer capacitors employ activated carbon, graphene, and carbon nanotubes or CNTs. Pseudocapacitors use conductive carbon-based composites, integrated with conducting polymers, metal oxides, and metal sulfides. Carbon electrode materials serve as major contributors toward the performance of the supercapacitor. Carbon materials, such as activated carbon, carbon aerogels, CNTs, and graphene help exhibit the electric double-layer capacitors, alright? The abbreviation of the electric double-layer capacitor is EDLC, and the abbreviation of the carbon nanotubes is CNT? Yep, CNT. In general, these carbon-based materials alone are electrochemically inert, and the energy storage only takes place due to the accumulation of the charges, ions on the electrode surface. The carbon or composite material-coated electrodes can act as active materials and/or collectors. In principle, carbon-based supercapacitors contain an electrical double layer formed at each carbon interface, where the carbon material is in contact with the electrolyte. When the supercapacitor is charging, the negative ions and vacancies on the cathode, and the positive ions and the electrons on the anode are arranged across the interface. This arrangement of ions and electrons, vacancies, during the charged state is known as an electrical double layer. Since the layer is composed of multiple ions moving, there is no major chemical reaction involved, such as in conventional batteries. This yields a superior charge-discharge life cycle. Porous carbon is used on the electrode to increase its surface area. The greater the surface area, the greater the charge that can be stored. Therefore, the supercapacitor with highly porous carbon nanomaterials is able to reach a higher capacitance. Cellular graphene, providing high electrical conductivity, a large surface area, and fully interconnected porous geometry, has attracted widespread interest as a support for complex three-dimensional, 3D, graphene hierarchical architectures. However, some limitations inhibit the potential of this carbon material as a building block for larger applications. Because of their irregularly distributed porous microstructures, cellular graphene maintains a low stretchability, proving to be a drawback for personal applications. The material's electrochemical performance is also dramatically affected by mechanical deformations under moderate levels of strain, limiting its viability in emerging wearable energy devices. In order to overcome these challenges, a mechanically guided 3D assembly approach must be taken to both control the cellular graphene architecture's physical structure and achieve the desired geometry. The approach would exploit stress release in pre-strained elastomer substrates in order to drive pre-designed two-dimensional, 2D, patterns to eventually transform geometrically into 3D architectures. When the applied device is biaxially stretched to 100%, the change in areal capacitance is negligible in the 3D supercapacitors. This is exemplified when after 100% cyclic stretching occurred 1000 times, the areal capacitance only changed 9%. An example of a specially designed, foam-based three-dimensional supercapacitor made up of porous graphene exhibited excellent electrochemical and supercapacitive performance. The special structure was layered with highly conductive electrodes, made from graphene ag-conductive epoxy graphene foam, forming an electrochemical double layer. The electrode was matched with the electrolyte H3PO4, where it yielded an aerial capacitance of 38 mF per square centimeter at 0.67 ampere per square centimeter, an energy density of 3.4 microwatt-hour per square centimeter, and a power density of 0.27 milliwatts per 1 square centimeter. The watt-hour, symbolized Wh, is a unit of energy equivalent to 1 watt, 1 W, of power expended for 1 hour, 1 H, of time. For power density is quantified as the amount of power processed per unit volume or unit area. One of the most typical units are watts per square centimeter or milliwatt per square centimeter. Both the electrode-electrolyte interactions and the energy storage are influenced by the surface area of the electrode, specifically, 618 square meter per 1 gram. The graphene foam-based supercapacitors, GFSCs, were bent under static and dynamic conditions and analyzed. The result was a stable graphene foam-based supercapacitors with up to 68% capacitance retention throughout 25,000 charging and discharging cycles. Yes? 25,000 charging and discharging cycles. The graphene foam-based supercapacitors was also incorporated into a flexible self-charging power pack by integrating a flexible photovoltaic cell that continuously powered a wearable pH sensor. Several challenges plague graphene-based fibers, including their loose porous structure, which causes low volumetric capacitance and an unsatisfactory wettability when in contact with electrolytes. An approach to mitigate this problem is the wet spinning of a non-liquid crystal dispersion of graphene oxide in CNTs. With the help of a capillary orientation apparatus and chemical reduction, wet spinning could be applied toward continuous hybrid fibers made up of reduced graphene oxide, RGO, fabricating CNTs as highly capacitive electrodes. The aligned CNTs aided the construction of a compact structure containing narrowly distributed mesopores within the continuous hybrid fibers. This enhanced the tensile strength of the fibers, improving internal electrical conduction of the fibrous electrode. Likewise, the RGO offered high pseudocapacitance due to its oxygen-containing groups. As a result, a higher volumetric capacitance of 355 F per 1 cubic centimeter and an energy density of 12 milliwatt-hour per 1 cubic centimeter at a current density of 0.1 ampere per 1 cubic centimeter was observed, while cycling stability of 94% was reached throughout 10,000 cycles, showing bending durability. The evidence showed the stability of the supercapacitor and possible applications for miniaturized flexible and stretchable energy devices. Self-healing, flexible electronics have a multitude of critical features that ensure long-term viability for personalized applications. There is a grand challenge in being able to realize high electroconductivity, mechanical resilience and viscoelasticity, inherent moldability, fast self-healing ability, and ideal electrochemical properties all in a device. For CNTs templated from nanocellulose and embedded in a viscoelastic polymer network, a dynamic crosslink between electrically conductive hydrogels was implemented. This synthesis was created by homogeneously dispersing carbon nanotube cellulose nanofiber, CNT-CNF, nanohybrids into a viscoelastic polyvinyl alcohol, PVA, borax gel matrix. The electroconductive hydrogels displayed quick self-healing due to the dynamic, reversible complexation done by borate ions, PVA polyvinyl alcohol chains, and carbon nanotube cellulose nanofiber nanohybrids. This carbon-based composite possessed capacitance retentions of 98% and 95% throughout 10 and 1000 breaking and self-healing cycles under different twisting, bending, and folding deformations, respectively. Based on these results, these materials have great promise for future applications in tailorable supercapacitors used in personalized electronics. There are still difficult challenges in the way of developing large-scale production methods for flexible carbon-based supercapacitor devices in arbitrary shapes, let alone at a reasonable cost. Screen printing can be an alternative to provide mass fabrication with patterning capabilities. For example, Graphene composite films printed on screens could be a viable solution to this problem. By combining the networked metal sulfide nanoflakes with reduced graphene oxide, RGO, nanosheets, the resultant material would be able to flex to the shape of any arbitrary solid-state hybrid supercapacitor. The films yield a high specific capacitance of 1739 farads per 1 gram at a current density of 0.5 ampere per 1 gram. This fabrication process can feasibly prepare fully printable supercapacitors and other electronic devices at a large scale, holding immense potential for the personalized technology field. Apart from applications mainly used outside the body, one important class of personalized energy devices are implantable devices. There is a need for these devices to have high flexibility, especially when implanting in or near a blood vessel. For this specialized approach, a sample of the fiber is implanted into the vessel while the wound can be sutured with fiber-like stitching. To achieve this, a flexible implantable fiber supercapacitor is able to be applied in vivo for energy storage. To fabricate these devices, a biscrolling process trapped poly, 3,4-ethylene dioxythiophene, poly, styrenosulfonate, PEDOT, PSS, ferritin nanoclusters in multi-walled CNT, MWCNT, sheets which are electrically conductive and have high mechanical strength. The multi-walled CNT sheets used were taken from a spinnable multi-walled CNT forest grown via chemical vapor deposition, CVD. An important aspect to take into account is the device's biocompatibility. It should be noted that this concern is important, especially when carbon-based surfaces will come in contact with complex fluids and tissues. The MWCNT sheets could be coated with biocompatible materials, such as PEDOT, PSS polymer and ferritin. This was seen in an in vivo application where the abdominal muscle of a mouse was stitched with a suture resembling a micro-diameter-sized fiber supercapacitor. The aerial capacitance of the PEDOT, PSS polymer? Ferritin? Multi-walled CNT-based fiber supercapacitor in a phosphate buffer saline solution was 33 millifarad per 1 square centimeter, with an aerial energy density of 0.82 microwatt-hour per 1 square centimeter. This showed an increase over the guest-free multi-walled CNT yarn, yielding values 52 times greater than the latter. Within the mouse, the supercapacitor exhibited biocompatibility and successful operation, seeing as how the capacitance maintained above 90% after 8 days in vivo. Next episode, we'll continue to discuss further how to move biofuel cells, or BFC, toward personalized platforms. Be sure to listen all the way through for the details. Do you have questions or comments? Or want to ask a question on a future episode of Podcasting Q&A? Hope we can find time to continue it soon. Please feel free to leave your comments here. Thank you.